Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand how to run repeated measures ANOVA in STATA. Repeated measures ANOVA is a statistical technique used to analyze the data where the same subjects are measured multiple times. That is, measures are taken at more than 2 time intervals under different conditions. This method is particularly useful for studying changes over time or the effects of different treatments on the same group of subjects. We'll try to understand this concept by a small example. An individual is undergoing the weight reduction treatment. To measure the effect, weight is taken at 3 different time intervals. So, the first treatment, you can see that the weight reduction treatment is not effective. The second treatment, so here weight reduction treatment is effective. This is repeated measures ANOVA. What are the key assumptions of repeated measures ANOVA? The first one, normality. The dependent variable must be approximately normally distributed at each level of within subject's factor, that is at each time point. Sphericity. The variances of the difference between all pairs of within subject conditions, that is the time points, must be equal. Independence of observations. Observations between different subjects must be independent. No outliers. Extreme values should not exist within any subject across the time points. Homogeneity of the covariance matrices. That is, if between subject factors are included, then the covariance matrices should be similar across the groups. So this is our data. I'll request all of you that please enter this data manually in Excel. So the subjects are 8, 1 to 8, and there are 3 test scores. Test taken at time 1, test taken at time 2, test taken at time 3. So please pause this slide and enter the data in Excel. In what format? Just see this format. So in this format, you enter in Excel. Now we will import this data set in STATA. So for this, we will go in STATA. I will save the file with the name of repeated measures ANOVA. I'll go in File, Import, Excel spreadsheet, click on it, Browse, the repeated measures ANOVA. You can give any name, click on it, press Open. So in the first row, subject, test 1, test 2 and test 3 will appear. Now click here, import first row as a variable names. Click OK. And the data has been imported. Now run the command browse. So you will be able to see the data which we had entered in Excel. But this is in wide format, and we want to convert it into the long format. Let's understand this concept. So this is a wide format, and we want to convert it into the long format. Why it is necessary? STATA's ANOVA command for repeated measures only works with the long format data. So we have to convert it, and how we can do it? There is a command, reshape long test I subject J time, rename test score, label, define time 1 as test 1, 2 test 2, 3 test 3, and label values time and time. So let's run this. So I've entered the command here. Now press enter. Again run the command browse. You can see it has been converted into the long format. Now what are our hypotheses and research question? Let's see. So the research question is, does the test score, that is the performance of students, vary over the 3 time points? Null hypothesis. There is no significant difference in test scores across the 3 time points, time 1, time 2, time 3. HO is mu1 is equal to mu2 is equal to mu3. Alternative. There is a significant difference in test scores in at least two of the three time points. So H1 is at least one pair of time points has a different time scores. So first we will have to check the assumption, and the first assumption is test of sphericity. The null is the variances of the difference between all pairs of time points. That is, test 1 to test 2, test 1 to test 3 and test 2 to test 3 are equal. This means that the sphericity assumption is met. This is null. Alternative, the variances of the differences between at least one pair of time points are not equal. This means that the sphericity assumption is violated. Now listen carefully. We will have to install these two packages. The first one is Mockley's. So SSC install Mockley, and the another one is SSC install Maheta. So run this command, install it, and then run stset subject, which will convert it into panel, and then run this Mockley score, comma, mtime. This will give you the Mockley's test of sphericity. So let's start with the first one of installing the packages. So SSC install Mockley, SSC install Maheta, enter. As I've already installed, it will give me the message that this package already exists. Okay, next one. We will have to convert, that is, we will have to run the command stset subject. So right here, xt set set subject, enter, and it will give you the message panel variable subject is balanced. Now run this command, Mockley score mtime. And we got the results. So this is a test of sphericity, and here is your p-value. What is the interpretation? Let's see. The p-value of Mockley's test of sphericity is 0.180, which is greater than the typical significance level of 0.05. This suggests that we failed to reject the null hypothesis of sphericity. In other words, the assumption of sphericity has not been violated, which is desirable. Let me do a small correction here in the spelling of Mockley's. So if the p-value is greater than 0.05, our null hypothesis, we fail to reject null hypothesis. This means that the sphericity assumption is met. This is desirable. And if the p-value is less than 0.05, the sphericity assumption is violated. This is not desirable. Okay, let's proceed further. Now we will run this command, ANOVA score subject time, comma, repeated time. So ANOVA score subject time, comma, repeated time, enter, and we got the values. So our results is reported in two parts. This is the first part and this is the second part. Let's do the interpretation of this one. See the p-values of the model, subject, and time. See these p-values. The repeated measures ANOVA analysis revealed a highly significant effect of time on test scores. Why it is highly significant? Because this p-value is less than 0.05, indicating that the performance changed substantially across the three testing periods. The highly significant mean effect of time confirms that the scores did not remain, the test scores did not remain constant across the three tests. The analysis revealed significant individual differences between subjects also, suggesting that the participants had varying baseline performance levels that persisted across the testing sessions. The overall model demonstrated excellent explanatory power. You can see it is 0.89, accounting for 89% of the variance in the scores, which remains strong at 81.98% after adjusting for the number of predictors. Now this same output can also be generated with the help of graphic user interface. Again, go in STATA, statistics, linear models, ANOVA, analysis of variance and covariance. Click here. Our dependent variable is score, model, subject, time, and here what is repeated? Time is repeated. So time, and click submit. You will get the same results. Just see here. Okay. See, it's simple. Statistics, linear models, ANOVA, analysis of variance, and just see independent variable, score, in model, subject, time, and time. So you got the output. Now let's proceed further. The next interpretation is for this part. So what is a null hypothesis? Null is there is no difference in the means of the dependent variable, it is a score, across the different time points. In other words, time has no effect. That is, mu at time 1 is equal to mu at time 2 is equal to mu at time 3. Alternative, at least one time point has a mean that is significantly different from the others. In other words, time does have a statistically significant effect. It's the same command which we have seen earlier. Now, which values to see? It will depend on the Mauchly's test, that is Mauchly's test p-value. This p-value. If the Mauchly's p-value is more than 0.05, you will have to see this regular values. I again repeat, if the Mauchly's test p-value is more than 0.05, you will have to do the interpretation from the regular uncorrected f-test results. And if the p-value of Mauchly's test is less than 0.05, we will have to go for the Greenhouse-Geiser correction factor. So what this thing is, as a p-value of the Mauchly's test in our case is more than 0.05, so we interpret from the regular result. See, what was the value? Let's check. It was 0.1802, which is more than 0.05. So we interpret from the regular result. Regular refers to the standard uncorrected f-test result. It is the initial calculation that assumes that the sphericity assumption has been met. In case, if the p-value of the Mauchly's test is less than 0.05, the Greenhouse-Geiser corrected results are to be reported. Now in any case, see, in any case, the p-values are less than 0.05. So what we will interpret from this? As a p-value of the standard uncorrected f-test is 0.00, which is less than 0.05, so we reject null hypothesis, which means that there is a statistically significant effect of time on the dependent variable. In other words, the test score, that is the performance of the students, significantly differs in the time period. We must conduct the follow-up test, that is a post hoc comparisons, to determine which specific time points differ from each other, that is time versus time 2, time versus time 3, time 2 versus time 3. Common tests for repeated measures include the paired t-test with a Bonferroni correction or the Tucky HSD test. The command line for doing the pairwise comparison is margins time. See, we are considering the time to be the significant factor affecting the dependent variable. So we want the margins time, pairwise compare effects, M compare Bonferroni, and we'll run this command. So enter, and you can see we have got the comparison of test 2 versus test 1, test 3 versus test 1, test 3 versus test 2. The same result can also be generated with the help of the graphic user interface. So for this, we will go in statistics, go ahead, try again, and here you will find the post estimation. Click on it. Now click on this test contrast and comparison of parameter estimates. Click on this pairwise comparisons. Click on this launch. Now from here, select time, and in multiple comparisons, select Bonferrone's method and press submit. And you can see the output which is generated. It is same. Now let's do the interpretation for this. The post hoc analysis using Bonferroni correction reveals significant differences between specific time points in the test performance. See the difference here. The difference in test 2 versus test 1, it is minus 78.5. P-value less than 0.05. It means that it is highly significant. Test 3 versus test 1, minus 89.37. P-value less than 0.05. It means highly significant. Test 3 versus test 2, minus 10.875. P-value more than 0.05 and it is not significant. Now how we will write? The comparison between test 2 and test 1 shows a statistically significant mean difference of minus 78.5, indicating that the scores decreased substantially from the first to the second testing session. Similarly, the comparison between test 3 and test 1 demonstrates an even a larger significant difference of significant decrease of minus 89.38 points, confirming that the scores remain significantly lower in the third test compared to the initial baseline. However, the comparison between test 2 and test 3, this one, shows no statistically significant difference as the p-value is more than 0.05. This non-significant result indicates that while scores drop dramatically between first and second test, they stabilize between the second and third testing sessions with no further significant decline. Now we require actual means of this individual test, that is test 1, test 2 and test 3. And we also require the margins plot. See, you can see the difference from test 1 to test 2, the decrease, test 2 to test 3. So from where we started, is there a significant difference or is there a significant decrease in weight after opting for the treatment? What is the command line? Margins time, margins plot. So either you can run margins time and margins plot, which will generate this type of result. And if you run tabstat score, statistics mean by time, it will generate this type of result. So let's run both of them. So right here, margins time. So test 1, its mean score is highest, test 2 lower than that, and test 3 lower than that. Now I want the plot for it. So margins plot, enter. So you will get the same result. See here, this one. Or you can run this command also if you want to compare the test scores. So tabstat score, comma, which statistics I want? Mean by time, enter. Now we will have to check the normality of the residuals. The command line is predict resid, comma, residuals, generate the histogram of it and run the formal Shapiro-Wilks test, which will generate this result. So for this, again, we will go in STATA. I'll write the command here, predict resid, residuals, enter. Now histogram, you can just write hist, resid, normal, and we will get the histogram. Now we will run the formal Shapiro-Wilks test. The command is swilk resid, enter, and we got this result. Now let's do the interpretation of it. We'll have to see the p-value here. as a p-value of the Shapiro-Wilk test is 0.528. See this one, which is more than 0.05. So we fail to reject null hypothesis, which means that the residuals are normally distributed, which is desirable. So this was all about how to run repeated measures ANOVA in STATA. For more videos on STATA, kindly refer to my playlist. I also uploaded many videos on data science, machine learning and artificial intelligence on my YouTube channel named Dhaval Maheta. To watch the full videos, please subscribe to my YouTube channel and check the playlist. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.